basicity. Means for all acids here, for example, when you take an acid like HCl and sulfuric acid, here we find one point of difference. HCl is having only one proton, and whereas sulfuric acid has two protons in that. And when you take phosphoric acid, there we have altogether three protons in this compound. Means when this acts as an acid, this can give us only one proton, whereas this is capable of giving two protons, and this is capable of giving altogether three protons to some other substance. So the number of protons which can be replaced, or the number of protons which can be given by an acid, that is called basicity of the acid. Now the term is basicity now. Basicity of acids. Means we can say that the number of protons which are given by an acid is called the basicity of the acid. HCl basicity is 1, sulfuric acid 2, phosphoric acid is 3 for us now. It doesn't mean that the number of hydrogens which are there in this will be always equal to basicity of the compound. For example, when you take, say, phosphorus acid is there, H3PO3. This is phosphoric acid and this is phosphorus acid. In this case, we have 3 protons. Here also we have 3 protons for us now. But here, basicity of the acid is 3 and it is only 2 in the case of phosphorus acid. Means one has to know basically the structure of phosphorus acid also in this case. That is to say, hydrogens which are bonded to highly electronegative element oxygen, they will be coming out in the form of acidic hydrogens. But whereas in the case of 3 hydrogens of phosphorus acid, only 2 of them are bonded to oxygen and remaining one is directly bonded to phosphorus, and that will not come out as acidic hydrogen. Therefore, if we have an idea regarding the structures, then we can know exactly the basicity of a given compound. Now if you take, for example, acetic acid is there, that is CH3COOH. In acetic acid here, though there are 3 hydrogens here and 1 hydrogen here, only this one hydrogen, that is CH3COOH. This hydrogen is bonded to this highly electronegative oxygen atom. This is considered to be acidic hydrogen. Whereas remaining 3, these 3 are bonded to only the carbon atom. So they will not be given out in the form of protons. Only this comes out as a proton for us now. So we can say in one word, any number of hydrogens which are directly bonded to highly electronegative elements, they can be considered as acidic hydrogens. So therefore in that way we can define the basicity of the acid. So number of H plus ions which are present in a given acid for us now. Then similarly one more term we have, that is regarding bases, that is acidity. Acidity stands for number of hydroxyl groups which are present in a particular base. Means for example, when you take sodium hydroxide, calcium hydroxide and say aluminum hydroxide. Now in sodium hydroxide, here NaOH, we have only one hydroxyl group that is present. Here we have 2 hydroxyl groups are there. In this case we have 3 hydroxyl groups are present. Means here in this case we define acidity as 1, acidity as 2, acidity as 3. So number of hydroxyl groups which are present in any alkali, that can be considered as a acidity there now. So this is regarding basicity and acidity. This is a second point regarding the main features of the Bronsted-Lowry theory. The first one what we have seen already is conjugate acid-base pair, and second point is a basicity and acidity of acids and bases for us now. Now next thing, now we are going to the third point. In the third point here, we are discussing regarding strengths. Strengths of acids and then bases. How we are defining the strength of acid and base in Bronsted-Lowry theory. Strengths of acids and base are defined with respect to, or in terms of Ka and then Kb, means with respect to the dissociation constants we are defining the strengths of acid and bases. Ka is called dissociation constant of acid and Kb is called dissociation constant of a base. Means for example, when you take acetic acid, if you consider its ionization in water, which is giving us acetate ion and hydronium ion here, no, H3O plus. Now when you are writing the dissociation constant Ka here, it will be CH3COO minus into H3O plus by we have acetic acid concentration and then the concentration of H2O we have. Okay, now let us consider the third point regarding the conjugate acid base pair here. That is, in Bronsted-Lowry theory, the third point is that we are explaining the strengths of acids and bases. Strengths are explained in terms of dissociation constant Ka and dissociation constant Kb for us now. So, depending upon the numerical values of Ka and Kb, we can say how far the acids are and bases are stronger. If we consider a simple dissociation of acetic acid here, which dissociates into say acetate ion and then hydronium ion here. When you are writing an expression for dissociation constant of acetic acid, we get CH3COO minus here and then H3O plus by CH3COOH and then H2O. All these concentrations will be at equilibrium concentrations only for us now. Now we already know that acetic acid is a weaker acid, thereby dissociation will be very much less. That implies the concentrations of these two will be very much less when compared to the concentration of undissociated acetic acid and then water here. So now we can say that numerically this value will be very much lesser value. Suppose when you consider acetic HCl, say which is giving rise to H plus and then Cl minus ion, and if at all we write the dissociation constant for HCl, this is going to be concentration of H plus into Cl minus by HCl for us. Since it has a greater tendency to give proton, concentration of H plus and Cl minus will be more, very much more than undissociated one. Thereby numerically this value of Ka is going to be very very high for HCl and the value of Ka is very much less for acetic acid. So once you know numerically the values of Ka and Kb, from that we can say which acid is stronger and which acid is weaker. So one word to say, higher the Ka value, higher the strength of the acid. Similarly, higher the Kb value, higher the strength of the base for us now. This is regarding the strengths of acids and bases which we have. Now coming towards the fourth point. Now the fourth point, it basically deals with the leveling effect of water or leveling effect of solvent we can say. Since normally we consider water, we write leveling effect of water in general. So it is leveling effect of water for us now. Now the meaning of leveling effect is whenever you consider all stronger mineral acids like HNO3, HCl, so on and so forth, they completely ionize in water. Means if you are taking say one normal HNO3, one normal HCl, say in water, so HNO3 in water we are taking, which is giving rise to hydronium ion and then nitrate ion we have. Similarly, when you take HCl also, say one normal HCl in H2O, this gives hydronium ion and Cl minus ion. Now whenever you take one normal of these two, they completely ionize and exist as hydronium ion. So whatever concentration you have here, everything is coming out as hydronium ion only. Similarly, in the case of HCl also, everything is in the form of hydronium ion for us now. Implies the nature of HNO3 and the nature of HCl, if you see in water, both of them are existing as hydronium ions only. So therefore, now we can say that strength of these two acids is becoming equal to strength of hydronium ion for us now. So therefore, we say that water is leveling or levels the strengths of both the acids to that of hydronium ion concentration for us now. Similarly, whenever you take in the base also, let us take sodium hydroxide or else potassium hydroxide and so on and so forth. So all these bases also completely ionize in water and they will be existing as OH minus ion. So it is irrespective of the nature of base you take in the aqueous solutions, all those strengths will become equal to that of the strength of hydroxyl ion concentration only. So this we can say that means water is leveling the strengths of all bases to that of hydroxyl ion and it is leveling the strength of all acids to that of hydronium ion concentration. This is called leveling effect of water. And this leveling effect is attributed to high dielectric constant of water. Means water is having a very much higher tendency to accept proton or it can give proton with equal ease. Due to that one we can say that all acids which are stronger than that of water and base is just stronger than that of potassium hydroxide and so on and so forth. Means it levels to that of hydroxyl ion concentration and hydronium ion concentration for us. This is regarding the fourth point in the case of Bronsted-Lowry theory.
శంకర్ గారి కెమిస్ట్రీ క్లాస్లో ఇప్పుడు చిన్న బ్రేక్ తీసుకుందాం. బ్రేక్ తర్వాత యాసిడ్స్ అండ్ బేసిస్ టాపిక్కు సంబంధించి మరిన్ని అంశాలను తెలుసుకుందాం.